All right, let's get into it. Today, we're going to tackle a classic coding challenge, one you see all the time in technical interviews, the sliding window maximum. Now, on the surface, it seems pretty straightforward, but trust me, finding an efficient solution requires a really clever insight. So let's dive in and break it all down. So here's how we're going to approach this. First, we'll make sure we really understand the problem. Then, we'll look at the obvious solution and see why it just doesn't cut it. After that, we'll get to the aha moment, the key insight involving a special data structure. We'll walk through the better algorithms step by step. And finally, we'll check out the code and see just how fast it is. Okay, so first things first. Before we can solve anything, we need to get a crystal clear understanding of what the goal is here. So here's the deal. You're given a list of numbers, right, an array, and you're also given a window size. Let's just call it K. Now, this window, it's going to slide across your array, one spot at a time, from the very beginning to the very end. Your job? For every single position that window is in, you have to find the biggest number inside it. Okay, that might sound a little abstract, so let's make it real with an example. Imagine our array is 1, 3, -1, ... and our window size K is 3. So for that very first window, 1, 3, -1, what's the max? It's 3, right? Easy. Now we slide the window one spot to the right. It's now 3, -1, -3. The max is still 3. Okay, slide it again, and now we have -1, -3, 5. Now the max is 5. See how that works? We just keep doing this all the way to the end. And this is super important. We're not looking for just one final answer. The goal is to build a whole new array that contains the maximum from each and every one of those window positions. So for our example, that final output we're trying to build is 3, 3, 5, 5, 6, 7. All right, so we get the goal. The question now is, how do we actually do it? Well, let's start with the most obvious way, the one you'd probably think of first. In programming, we call this the brute force approach. Seriously, if you didn't know any fancy tricks and just had to solve this, how would you do it? You'd just look at each window, find the biggest number, and write it down, right? And yep, that's pretty much what the brute force algorithm does. It looks at the first window, scans through all K elements to find the max, records it, and then slides the window over and does the exact same thing again. And again, and again, until it hits the end. It's simple, it's logical, and it definitely works. But there's a huge catch. And that catch is speed. It's just too slow. In what we call big O notation, this method has a time complexity of ONK. What does that mean? Well, if your array has n items, you're looking at about n windows. And for each of those n windows, you're doing K comparisons to find the max. So you end up doing roughly n times K operations. Now look, if your array is tiny, who cares, right? But what if you have 100,000 numbers, or 1,000,000? Suddenly, n times K becomes a massive number of calculations. In any real-world coding challenge or interview, this solution would just time out. You'd get that dreaded time limit exceeded error. We have to be smarter. And this is where things get interesting. This is where we find the key insight, that aha moment that lets us go from a slow, clunky solution to something elegant and fast. So here it is, the big idea. Once you have a window and you find a really big number in it, think about all the smaller numbers that came before it in that same window. Are they ever going to be the maximum in any future window? No way, because any future window that includes them will also have to include that bigger number we already found. So those smaller, earlier numbers, they're basically useless now. And that is the breakthrough. We don't have to remember every single number. We just have to keep track of the numbers that have a chance of being a future maximum. We can just throw away all the ones that have no hope. Okay, so that's a cool idea, right? Throw away useless numbers. But how do we actually, do that in code? Let's see how we can turn this insight into a real working algorithm. The hero of our story is a special data structure called a monotonic Deque. Okay, let's break that down. A Deque, spelled D-E-Q-U-E, is just a double-ended queue. You can add and remove stuff from both the front and the back. The monotonic part is our special rule. We're going to make sure the elements inside are always kept in a specific sorted order. For our problem, that's going to be descending order. So here's how it's going to work. Just a few simple rules. First, a really important detail. The DQ is going to store the indices of the numbers, not the actual values. This helps us know where they are. Second, the number at the very front of our DQ, that will always be the index of the maximum for the current window. Third, and this is the magic, Before we add a new number's index, we look at the back of the Deque and kick out anything that's smaller than our new number. And finally, we'll do a little cleanup. If a number's index has slid out of the window, we kick it out from the front. Let's see this in action. Right, let's walk through this. We start with the first number, 1, at index 0. We just add its index to our empty Deque. Simple. Next up is 3, at index 1. Now our rule says the Deque must be in descending order. Is 3 bigger than 1? Yep. So we have to pop index 0 out before we add index 1. Now our Deque just has 1. Then we get -1 at index 2. Is -1 smaller than 3? Yes. So we can just add its index 2 to the back. Our first window is now full, 1, 3, -1. The front of our Deque is index 1, which points to the value 3. And boom, that's our first maximum.
Okay, let's keep going. The window slides. Next up is -3 at index 3. It's smaller than the -1 at the back, so we just add its index. The max is still at the front, index 1, so our result is 3 again. Now for a really important step. We get 5 at index 4. First, cleanup. The index at the front is 1. Has our window slid past position 1? Yes, it has, so we pop it from the front. Now we process the 5. We look at the back of the Deque. Is 5 bigger than -3 at index 3? Yes, pop it. Is 5 bigger than -1 at index 2? Yes, pop it. The Deque is now empty, so we can finally add our new champion, index 4. The max for this window is, you guessed it, 5.
And you can see how this pattern just keeps playing out. When 3 at index 5 comes in, it's smaller than 5, so it just gets added to the back. The max is still 5. But then 6 at index 6 arrives. It's bigger than 3, so index 5 gets popped. It's bigger than 5, so index 4 gets popped. Then index 6 goes in. Our new max is 6. And finally, 7 at index 7 comes in, kicks out the 6, and takes its place as the final maximum. And just like that, we've built our final result array, efficiently, one step at a time. So we've seen the logic, we've walked through it. Let's bring it all together by looking at what this looks like in code, and more importantly, analyzing just how much of an improvement this really is. And here's the code that makes it all happen. You see that main for loop? That's us going through each number one by one. That first if statement, that's our cleanup rule, checking if the oldest element at the front has fallen out of the window. And that while loop, that's the real engine right there. That's the part that enforces our descending order rule, popping all the smaller, useless numbers from the back before we add the new one. It's a perfect translation of the logic we just walked through. And here, my friends, is the payoff. Just look at that difference. The brute force method was O(n) times k. Our new, shiny, monotonic Deque solution, it's O(n). That's not just a little better. That's a massive improvement. It means the time it takes to run grows directly with the size of the input, not exponentially. This is the difference between a solution that passes and one that fails. Now, you might be looking at the code and thinking, wait a minute, there's a while loop inside a for loop? Isn't that O of n squared? And that is a fantastic question. But here's the trick. Think about any single element from our array. Its index gets added to the Deque exactly one time, and it gets removed from the Deque exactly one time. Since each element only gets processed at most twice, the total number of operations is proportional to n, the number of elements. That's how we get that beautiful, efficient, linear time complexity. So there you have it. We took this sliding window maximum problem, saw why the simple approach fails, and used a really clever data structure, the monotonic Deque, to build a highly efficient solution. But the biggest takeaway here isn't just this one problem, it's the pattern itself. This idea is incredibly powerful. And that brings me to a final question for you to think about. Now that you know this technique, what other kinds of problems involving ranges or windows or finding minimums and maximums could you solve with this exact same clever approach?